Chapter 6, Bending Formula Derivation Part 2. So again, consider a cross-section, handle a positive moment of m as shown in the figure below. So this is a positive moment again, which pushes the top. So this is a push at the top section, and it shows a bending stress variation. This is a stress, but due to bending. Mhm. And we are going to derivate the a final a formula. If you remember in previous video, we just stopped by the location of neutral axis based on force four formula, and we just want to expand our derivation to get the final formula for bending. So a bending moment is integration of an arm times force. So a moment is equal to an arm times our force. So this is our arm and this is our force. Mhm. So this is our df, this is our moment, and this is our uh, phi. So we'll get back to this a negative here soon. Just let us move on. And if you do so, it just gives you, and if you replace sigma x by the force formula from previous video, which I will provide you with the link at the end of this video if you have not reviewed that one, and that's a negative y over c times sigma m, and that's dA. Mhm. And that gives you m. A moment is just take the constant out of integration, that's sigma max over c, and inside the integration is y squared dA. And if you remember, y squared dA is the second moment of our area, or a moment of inertia. Do you remember that from previous chapters? Mhm. And if you just replace that in the moment, that's a sigma max over c times moment of inertia. If you rearrange the equation based of sigma max, it gives you m times c over I. Mhm. And that's a bending stress, maximum bending stress due to bending. Mhm. Note, moment about z-axis, which gives us a sigma a. Mhm. Do you remember I apply a negative and put a asterisk sign there, and I told you we'll get back to that. So let's see how that negative comes to play. So the minus sign says if we use a tensile stress which sigma x is greater than y in tension, it gives you a negative moment, which is not our case. This is a negative moment which pulls the top, but our case is a push at the top section, as you can see in the figure and also in the moment sample. Hmm? So that's why we need to apply a negative to that equation to cancel out the negative in the formula of sigma x to give us a correct positive moment, which gives us a push at the top section. That's the reason of that negative uh, y in a previous slides here. There is a negative in the formula of sigma. That's why we use that. Mhm. If we want to calculate the curvature and radius of curvature, we know sigma x is a negative y over c times sigma max. Mhm. And sigma max is, just rearrange it based on sigma max, x minus c over y times sigma x. And at the same time, from previous part, we get the equation for bending that sigma x is equal to mc over I. Mhm. So sigma m is both minus c over y sigma x and also mc over I. So if you cancel out c from both equation and rewrite it based on sigma x, it gives you sigma x is minus my over moment of inertia, and let's call that our sixth equation. And also from equation 2 from previous video, we do know epsilon is c over rho, and then 1 over rho is equal to epsilon m over c. You just rearrange the equation, you get that. And epsilon m over c is equal to sigma over e times c, a denominator, and that's equal to mc sigma m is just mc over I. And if now we cancel out c from both numerator and denominator, it just gives us 1 over rho, it's m over ei. And that's our seventh equation. And that's nothing but the curvature, and rho itself is the radius of curvature. So how that goes? The radius goes by rho, that's the radius of curvature, and 1 over rho is the this is radius of curve, and this is curvature itself. So it means if we want to get a curvature of 0, mhm, 1 over rho is equal to 0, almost 0, we need rho to goes to infinity. Mhm. So like Earth's planet has a radius of a high value for radius. That's why when it comes to the curvature, 1 over r, r is a huge number, a 10, if I'm not wrong, that's 10,000 kilometer or something like, it's almost, if I'm not wrong, 10 400 kilometers, something like that. I'm pretty sure that's about 10,000 kilometers. But the point is, if R is it's going to a very high number, you don't feel that curvature. That's a curvature of about almost zero, almost zero. You cannot feel that if rho goes very high. And let's make a comparison between what we have in stress and also in deformation. So first in from what we learned from axial torsional torque and axial load torsional torque and a bending moment. So in the first case, a axial force is sigma p over a. Sigma is normal stress and A is cross-sectional area. P is just axial force. In a torsional torque condition, tau maximum shearing stress is Tc over J, and J stands for polar moment of inertia in chapter 5. And in bending moment in chapter 6, sigma max is maximum stress due to a bending moment is just mc over I. And that's interesting if you just connect the dot between torsional torque, tau is Tc over J in torsion, and sigma max is mc over I in a bending moment. And when it comes to the right, to the deformation, it's even more interesting. Delta in axial deformation due to axial load is PL over EA, and E was just a modulus, elasticity modulus. And when it comes to a torsion, phi, angle of twist or torsion is TL over GJ, torsional torque times the length of shaft over rigidity modulus times a polar moment of inertia. And when it comes to a bending moment, delta is a negative ml over ea times y, and that's deformation due to a bending moment. And a comparison between them, it's a deeper understanding of what's happening in the chapters we already reviewed in terms of stress and both and deformation. Let's go by a new definition of elastic section modulus. Sigma m maximum is mc over I. We learned it from this from today, and elastic section modulus goes by I over c. So it means if in this equation, in the same equation, if we just consider I over c equal to s, it just says sigma max is m over s. And that s just stand for elastic section modulus. So sigma max is m over s. So in a case that if, in a sense that if you can increase section modulus, you can reduce sigma max in a design. So for a rectangle with B and H, I is 1/12 base cube height, C is H over 2 if C is just halfway through, so C is H over 2. So a section modulus is 1/6 of BH square, and that's a 1/6 of B is 1/6 of A times H. And if you just consider that in a two element of A and B with the same amount of area, so 6 times 4 is 24 inches squared, and a 3 times 8 is also 24 for B. So both of them has the same area. The one which has a higher height goes by a higher, so definitely SB is higher than SA because height of B is higher than. That's how we can play around with the uh, section modulus to go with the uh, design element. Thank you.